This is topic 9.7, galvanic and electrolytic cells. The objective is to explain the relationship between the physical components of an electrochemical cell and the overall operational principles of the cell. We're going to look at some things, like some terminology you should be aware of. Electrodes, anodes, cathodes, salt bridge, half cell, half reaction, voltage, current, etc. Electrical energy can be generated from a chemical reaction. In oxidation-reduction reactions, electrons are transferred from one species to another. So a way to harness this is to use an electrochemical cell. And it's set up as shown below. You have two beakers, and you have a salt bridge containing them, connecting them, I'm sorry. You also have your anode and your cathode. And along the anode and cathode, you could say you have something for the electrons to travel on, and it produces a certain voltage. So in your half cell, or in a beaker, there's a metal or some kind of gas system, and it has some corresponding ions in solution. So you'll notice that on the left side, the anode, you have your silver on the silver metal, and then you have it's in a solution of silver nitrate, which which contains silver ions. On the other one, you have a solid gold, with in a solution of gold nitrate. So both of them undergo different reactions. They're either going to gain or lose electrons to oxidize or reduce, and that's something you're going to be able to kind of piece together. The electrode where oxidation occurs is called the anode because it attracts anions from the salt bridge and the solution. The electrode where reduction is occurring is called the cathode because it attracts the cations from the salt bridge in the solution. The way to help remember this, red cat, anox. So electrons flow through the wire from the anode to the cathode, fat cat from anode to cathode. The salt bridge is used to separate the solutions. The ions in the salt bridge will travel through the solution and serves to maintain a neutral charge as electrons flow from one side to the other. Without these ions in the salt bridge, there would be nothing going on. A porous disc between the beakers works similarly, but we'll just focus on the salt bridge. To predict which of the potential reactions is considered thermodynamically favorable, we need to look at a standard of reduction potentials. You'll be given those on the test, and I'll show you those for each problem that you do for your homework or in this lecture. It's basically a ranking of different substances. The ones that are best at reduction are at the top. This is important. They're most likely to be reduced. With the substances that are worst at reduction, they're the ones that are most likely to be oxidized. The electromotive force or reduction potential gives voltage that is generated from the half reaction. Oops. So let's look at two substances. We have silver and gold from there before. As it is written in the it would be given to you. You have the reduction reaction, and it gives you the reduction potential. The one that is the larger number, that is the one that's going to be the one that's better at reduction, and that stays the way it is written in the table. The reason why I say that, because the one that is better at oxidizing, or the one that's lower in a reduction potential, is going to be flipped and written in reverse. So what you do now is you need to combine them, but before you do that, you need to flip your oxidation reaction to be able to cancel out the electrons. And you see that when you do this, that there is a kind of an imbalance, so to speak. There's only one electron in the silver reaction, and the gold one has 3, so you need to multiply by 3 to get rid of the electrons after you flip them. So we'll go through an example together. So after you do that and you combine them, you see that the way that it's written, with the gold 3 plus producing solid gold, and the silver producing silver ions, this will react, and it's going to be considered thermodynamically favorable. And it includes the favorable reduction reaction. If it's written the other way, it's not considered thermodynamically favorable. Excuse me. So that's the part about flipping and all that type of stuff makes sense. However, here, when the reaction is flipped or when the reaction is multiplied by a factor, you do not change the voltage. So don't do that with this one. So they may give you an answer where you do that and you think you're doing the right thing, but you're not. So when you're dealing with cathodes and anodes and having to flip a reaction, that's fine, but do not multiply the voltage by the number that you distributed. So you see that now, after doing the reduction and the oxidation, recognizing what it is and flipping it, your reduction potentials are still 1.50 volts, but also now it's negative 0.80 volts. The thermodynamically favorable reaction will generate 0.70 volts. Cells that are thermodynamically favorable have positive voltages and are known as galvanic or voltaic cells. So some terminology there. So this is how you would get it right here. 1.50 plus the negative 0.8. Negative 0.80. If you have the unfavorable reaction, you're actually going to make negative 0.70 volts, and it will require that amount of volts to power up. Cells that are considered thermodynamically unfavorable have negative voltages, and they require external power cells, and they need power supply, and they're called electrolytic cells. So some good terminology to keep in mind. Given these two reduction half reactions, letter A, write the thermodynamically favored balanced overall reaction. So first we have to recognize who is going to be reduced and who's going to be oxidized. So we see that the top one, I'm not saying it's always going to be like that, but just something to look out for. Maybe, maybe not. This is technically the larger number, so that's going to stay the same. The other one needs to be flipped to balance it out. So I'm going to look at this, and I'm going to see, okay, so my magnesium 2 plus aqueous plus 2 electrons produces Mg solid. So I look, and I'm like, okay, what do I need to do with that sodium one, the sodium half reaction? I need to flip it and then multiply it by 2. So let's see. Where are we at? Okay, so I need to flip this, so it's going to be 2Na solid plus 2Na, oh, sorry, arrow, sorry, 2Na 1 plus aqueous plus 2 electrons. So I'm going to add these together, and my 2 electrons cancel out on each side, so I'm left with the following. I don't know where I'm going to put this. Magnesium 2 plus aqueous plus 2Na solid produces Mg solid plus 2Na plus, oh golly, aqueous. Sorry, I don't have space. Now I'm going to rewrite this up here so you can clearly see it. Hopefully clearly see it. Magnesium 2 plus aqueous plus 2Na solid produces magnesium solid plus 2Na plus aqueous. Now I'm going to erase all of this stuff. There we go. Calculate the voltage for this cell. So essentially you're going to add these. But be mindful though, so the overall voltage, how do I get that? So I'm going to take negative 2.37 volts. I'm going to add it to the opposite because I flipped that one. So it's going to be 2.71 volts. It's going to give me positive 0.34 volts for my answer. Write the reaction that occurs at the anode. The anode, that is where you have oxidation. So of the two, which is the oxidizing one? It's going to be 2Na solid produces 2Na plus aqueous plus 2 electrons. Write the half reaction that takes place at the cathode. So it's the opposite. It's the one that's where reduction occurs, and we didn't need to flip that, so we're just going to write it as is. So magnesium 2 plus aqueous plus 2 electrons produces magnesium solid. After the reaction has been allowed to take place, what will happen to the anode? So the anode will dissolve in solution as it forms sodium ions. It will decrease in mass. After the reaction has allowed to take place, what will happen to the cathode? So the cathode actually will, according to this reaction, if we're looking at the cathode reduction, so notice how we're going to form magnesium solid. So the cathode will increase in size as magnesium metal forms. It will increase in mass. Given these reactions, what's going on here? So write the thermodynamically favored balance over reaction, calculate the voltage, write the half reaction that occurs at both the anode and the cathode, etc. So not too bad. This is very doable. So I look here, remember that the higher value for my potential, that is where reduction is going to occur. So my reduction is here. That means that is going to be my reduction, and that's my cathode. Here, this is going to be oxidation, and this is going to be my anode. So because it has a lower reduction potential value, so what I need to do is I need to flip this and see if I need to multiply by anything, which I don't because I have 2 electrons now on both sides when I combine them together. So write the thermodynamically favored overall reaction. So I have my two, this is going to be an acidic, so I have two hydronium ion aqueous plus 2 electrons produces hydrogen gas and water liquid. I have iron 2 plus oh sorry, I need to flip that actually, I'm sorry. So I have iron solid and I produce iron 2 plus aqueous plus 2 electrons. So I don't need to multiply by anything. I do need to cancel this. So I end up with a total, so to speak. So the reaction is going to be 2H3O plus aqueous plus iron solid produces Fe2 plus aqueous plus hydrogen gas plus water. So calculate the voltage for the cell. So I have 0. So I'm just going to add the two. 0.00 volts plus the opposite of what I have up there for the second one. So my answer is going to be plus 0.45 volts. Write the reaction that takes place at the anode. So this is my oxidation. So at the anode, I'm going to have solid iron forming. It's going to be going into solution. So it's going to form Fe2 plus ions. Write the half reaction that takes place at the cathode. So is this going to be the 2 hydronium ions plus aqueous plus 2 electrons producing hydrogen gas and liquid water. So what will happen at the anode after reaction occurs? So if you see that what happened to the iron at the anode, it is actually going to decrease in mass. The iron anode decreases in mass as it dissolves into solution. After the reaction is out of the place, what happened to the cathode? So notice though, in my cathode, I don't form a solid, so it can't be like the last one where we say, oh, the cathode increases in size. So what will we notice if we have hydrogen gas and water? So we're going to see the formation of hydrogen gas bubbles. Alrighty, if you have any questions, please let me know. Thanks.